Section 7.5 deals with the work kinetic energy theorem, which is key to this section on energy. All right, so let's work up to it. We have defined work to be the integral of f dot dr. Let's just consider it one-dimensional so that we don't have to deal with the vector stuff right now. If we consider just the one-dimensional case here, we can drop all the vector stuff and we're just left with f dr. So applying Newton's second law, we can say that the sum of forces is ma. And we know that the acceleration is dv dt. So let's do that. Now, the next thing we're going to do is apply the chain rule. By applying the chain rule, we can say that dv dr dt is the same as dv dt. But now we recognize that dr dt is just v, and we've got a dr, which is just 1. So we have, that leaves us with a v and a dv. All right, if we now integrate this on arbitrary boundaries, say from a to b, we're integrating with respect to v, so we're left with m v squared over 2, evaluated from a to b. And if we evaluate from a to b, then we have 1/2 m v a squared, or sorry, vb squared first, minus 1/2 m v a squared. Right, initial and final values of velocity. So I guess I should even do these as v's with subscripts for initial and finals, right? All right, so this brings us to the definition of the work kinetic energy theorem. So we just said that the net work on an object is equal to 1/2 m v final squared minus 1/2 m v initial squared. And this form is what we define to be the kinetic energy. 1/2 m v squared. So we can now say that our work net is equal to kinetic energy final minus kinetic energy initial, which is just the change in kinetic energy. And that's our statement for the work kinetic energy theorem, is that the net work on a system is equal to the change in kinetic energy of that system. Right, it seems a pretty simple statement, but it's very powerful, and we're going to use it a lot in solving problems in new ways where we don't have to use kinematics or where it's not convenient to use kinematics. All right.